Hi, my name is Grant Jennings, Director of International Marketing for Gowin Semiconductor, and today I'm going to be talking about GoAI 2.0, which is a machine learning inference solution, including all of the necessary software as well as a processor dedicated for machine learning, targeting edge applications. First, I want to just talk briefly about some of the benefits of FPGAs and how it applies to doing AI at the edge. So FPGAs are really good at doing parallel computations and pipeline computations. So parallel computations are basically when you're computing two or more things at the same time, and FPGAs, being a gate array, allow you to do just that. You can do multiple calculations at the same time. Also, you can pipeline computations, specifically computations of exactly what you want, clock cycle by clock cycle, and at fairly high speeds. So, say at 100 megahertz, you can, in real time, be manipulating uh, video data, for example. And this allows you to do things that, unlike a processor, where even if it's running at, say, 100 megahertz, it may take many clock cycles of that 100 megahertz to do a particular computation. In this case, we can pipeline the computations to do that, to do the computation clock cycle by clock cycle, and have another set of data coming in right after. Number two, several multipliers are in the device, and this is great for convolutional filtering. So you can do many multiplies at the same time, and you can also pipeline those multipliers. Three, several memories are available for storing coefficients and storing layers. Now, this not only includes memories within the FPGA, but interfacing to external memories such as PSRAM or DDR and external flash. Also, the block memories can be used both as RAM and flash. Number four, flexible interfacing to connect many types of different inputs. So FPGAs are really good at interfacing, meaning that you can connect cameras, microphones, biometric sensors such as accelerometers, and other interfaces as well. These cameras can be source synchronous or parallel, and you can use the FPGA to buffer data or say frame buffer data for video, a common application. You can buffer microphone data for processing, say, spectrogram on the front end, and same with the accelerometer. So you have this flexible interfacing, flexible memory, many multipliers, and the ability to do high-speed parallel computations. So what is GoAI 2.0? GoAI 2.0 is a machine learning platform specifically for inference. Train models that are set up to detect certain features within an environment from sensors. So a sensor being a camera, a microphone, or an accelerometer, and using convolutional neural networks in the device, we can detect or infer certain things in that the sensor is seeing without the need for internet connectivity. And so this really comes in two parts. One part is the software needed to go from machine learning environments such as TensorFlow and all the way down to optimizing and quantizing those models, those trained models that you have in TensorFlow, and then deploying them on Go and FPGAs. Second part is the hardware part itself. And so with GoAI 2.0, you have a machine learning processor that can process multiple layers of convolutional neural networks in the FPGA and using the framework of the software element that's also included with GoAI 2.0. Some of the advantages of GoAI 2.0 is that it offers high flexibility and adaptability. So one example of this is the radical changes that are happening within TensorFlow itself. Even in the last 6 months, we've had to update GoAI 2.0 to accommodate new revisions within TensorFlow and TensorFlow Lite. The ability to buffer data, buffer data in memory, and then also be able to handle various types of front-end processing is also shows the flexibility and adaptability of GoAI and using FPGAs. So, for example, you can take in camera data and buffer it so it can be held for the neural network processing. Um, Processing audio data in the form of a spectrogram so that it can be ready for the convolutional neural network processing. These are all things that can happen in the FPGA and complement the capabilities of GoAI. Second, and a major benefit is that you can use Gowin's low-cost, small form factor, low-power FPGAs to leverage GoAI. So our flagship device that we typically use for this application, although you can use any Gowin FPGA, one of our really flagship devices for this particular solution is our GW1NSR4 device. And this device is a 6mm by 6mm FPGA in an easy breakout QFN48 package, and it provides processing in under 20 milliwatts for GoAI 2.0 with 8 megabytes of extended memory for doing very deep layers, very deep convolutional neural network layers. And it includes control with a Cortex M3 hardcore. Just a really great device that really meets the profile of doing edge AI. And three, easy to use. So the GW1NSR4 has a hardened Cortex M3 processor, like I mentioned, and this is really great because it provides control and pre-processing, control, and determination of what to do with your inference output, all from an easy to use Cortex M3 hardcore. On our larger devices, we actually use the Cortex M1 softcore, and so within the ARM environment, you have a very easy to use processor that can control your GoAI 2.0 machine learning processor. Second part of easy to use is that we adapted the TensorFlow flat buffer integration. So what this is TensorFlow has a secondary portion called TensorFlow Lite for microcontrollers. And what it does is it quantizes a pre-trained machine learning model and then optimizes it. And that allows it to, in some cases, target a microcontroller. But what we do is we actually extract that flat buffer file and then use that all the information from that flat buffer file to target our specific GoAI 2.0 processor. So a much more optimized processor specifically for machine learning at the edge, and it can the TensorFlow flat buffer files can be parsed to just basically load them into the device and use it. Then lastly, under easy to use, one platform can be used for many uses. So the same GW1NSR4 device with the same bit stream can actually be redeployed with a different image sensor, different microphone, different IMU, and you can cover a lot of different use cases with the exact same FPGA. So you can do image detection with a camera. You can do audio phrase detection with a microphone. And you can do gestures in the air by holding an accelerometer and doing detection of gestures. So one device, one PCB, such as the GoAI embedded boards that I'll show later, can be used for a variety of different edge inference applications. Okay, a little bit about GoAI 2.0 software. So, GoAI 2.0 software leverages TensorFlow and Keras, and you can use the same environment that most uh, data scientists and machine learning engineers are used um, to train and test your machine learning models. So nothing new there. Same framework, lots of information on the web, kind of the de facto standard, uh, one of the de facto standards in terms of um, doing machine learning. Once you have that trained machine learning model, you can use TensorFlow Lite for microcontrollers to create a flat buffer or TF Lite file. So those are the same thing. Flat buffer, basically the extension is TF Lite. And this is a file that is the same model, but it's quantized and optimized for embedded hardware. And then we support unsigned integer as well as 8-bit integer for your input and your input and output layer values. And so this is pretty common, and this is built into TensorFlow under TensorFlow Lite. And then in terms of FPGA deployment, we have software tools that target Windows and Linux. And basically, we run some scripts on the TensorFlow Lite file to generate 3 output files. The first output file is an MCU firmware file. And what this does is it initializes and controls the machine learning processor. The second file is the FPGA bitstream itself. This defines the input interface, whether it be a camera, microphone, or an IMU. It also instantiates the microcontroller, and then it also instantiates the GoAI 2.0 machine learning processor. The third file is a ROM or flash file that's stored in SPI Flash that actually has the coefficients for each layer of the model. This is just another diagram of the solution flow, of the software solution flow. So you train your model, and then you optimize it using TensorFlow Lite and generating a TF Lite file that quantizes and optimizes the model. And then the files are that TF Lite file is parsed, and you generate the 3 files mentioned earlier that allows you to deploy onto a Gowin FPGA. So just a little bit deeper into the GoAI architecture, hardware architecture, and the processor. So just to kind of explain how this 3-file system works a little bit more, just starting at the top, you have your ARM Cortex M1 or M3 processor, and it has some instruction and data memory. This memory doesn't need to be very large because all it does is it loads the parameters needed for each layer, which is a register set, a register map, and then it controls which layer it's on, basically by starting the processor, the machine learning processor, and then waiting for an interrupt back. It also has the ability to read the machine learning processor's scratchpad memory and write to it. So after the machine learning processor is done with the final layer, you can actually read out the last layer, which is actually a result, do any additional processing if needed, and then decide to, blink an LED or send some information out of a SPI port, whatever you'd like to do. On the left-hand side, we have the camera and microphone or accelerometer input, and that the data of that sensor goes to a data buffer, and that data buffer can vary in size depending on the model, but we by default provide a 96 by 96 byte input buffer, and that's accessible through the Cortex M processor through the memory map. And then on the right-hand side, you have the GoAI 2.0 machine learning processor itself, which includes various design modules to handle the computationally intense functions of a machine learning convolutional neural network model. And then you have a memory controller that either can use internal PSRAM if it's in one of the Gowin FPGAs that has internal PSRAM. Those are the R series devices. And then also there's a SPI flash controller that accesses the weight and bias coefficients for each layer of the model. So just to look at this in a different light, the white picture in white here is showing the inputs, or is showing a kind of a diagram of a convolutional neural network. And the circles in blue are kind of the inputs. So this would be like, let's say you're doing camera data. Well, this would be the camera data itself for one frame. And then the green circles would be the end of your convolutional neural network, which should have your inference result. And then the middle layers are just that. They're layers, and so they're kind of the intermediate processing of various filters that go on between layers. And so the input data buffer we can see in the upper left-hand diagram, same diagram as the previous slide, it holds that first layer of data, the input data layer. And then the in-between layers are held in the PSRAM, and there's the PSRAM is arbitrated such that there's a portion that's for the input data, and there's a portion for the output data. And so the PSRAM dictates how deep, how many filters you can have per layer. And fortunately, with the Gowin FPGAs, this PSRAM is very large. So within the device, you have 8 megabytes of PSRAM. That means that you can have an input and output layer up to 8 megabytes in size. That's huge. So very deep layers are possible with GoAI 2.0. And then the instruction and data memory, basically that determines the number of layers in which you can do. So all this does is it just holds some parameters for each layer. And since the coefficient data is stored in SPI flash, that's really offloaded from the processor, and the instruction memory just basically holds the parameters for how to control each layer. So now let's talk a little bit about GoAI 2.0 hardware. Just out of the box, we kind of support 3 primary devices. There's not really a one-size-fits-all solution here, but our flagship device is our GW1NSR4 device, which I mentioned earlier. That's that 6mm by 6mm device in the very easy to break out QFN48 package. Then, if you want to use GoAI amongst other capabilities within a system, you may need some more resources. And so we also support our GW2A R18. So this still has the embedded PSRAM, and we target a 10mm by 10mm QFN easy breakout package as well for that. The interesting thing about this device is that it actually has 8 megabytes of PSRAM, but it's over 2 ports of 8-bit ports each. And so this can make it interesting because of cases where you may want to do 2 different types of models. Let's say you wanted to do audio phrase detection and image detection. Well, you can have 2 independent systems and still use that internal PSRAM in this case, it's separate. It's partitioned differently. It's partitioned into two 8-bit memory blocks. And then lastly, we support our GW2A55. And really, we picked a 484 BGA. So for high I/O count cases, this is where that would be a good fit. Interfaces, we just out of the box, we support one camera, one microphone, and one IMU. Of course, in all these cases, you can choose different FPGA packages and different cameras, different microphones, different accelerometers. But if you stick with these, that's gonna allow you to accelerate your development as fast as possible with minimal additional overhead in terms of engineering work. So, you know, some cases you can't stick to this, but it's nice to know what works so you can start with that and then change from there. Architecture wise, I mentioned the 48 megabytes of PS RAM for the accelerator, 8 megabytes of flash. That's adjustable. It's just external SPI flash, so you can adjust that to whatever you need. And then 2 to 16 kilobytes of processor RAM. That's also adjustable. It's just based on need. So if you want to do something else with the processor, or you wanted to pre-process some input data, you can do that. And boards, I'm going to show those in a later slide, but we have boards specifically for GoAI targeting each of these devices. So now this is a picture of the GW1NSR4P GoAI embedded development board. You have 4.5K lookup table FPGA, hardened Cortex M3 processor, 8 megabytes of internal PS RAM, easy breakout QFM48 package, and then you also have the camera, the microphone, and the accelerometer to do all of the demos that we feature. And that also includes the external SPI flash as well as an HDMI TX port for showing some output data for demonstration or development purposes. Second board is our AR18, GWAR18P embedded development board. 20K lookup tables on this FPGA, so a little bit more. You have the 10 millimeter by 10 millimeter easy breakout QFN package. And then you have your camera. You also have your microphone and IMU, I believe, on this board. And this board includes HDMI RX and HDMI TX. So you get HDMI RX on this board as well. So that makes it good for, let's say that you want to, for development purposes, have some video stream go through the board. You can do that. You have an internal 4 megabyte PS RAM times 2 in this case, I believe. So you actually have 8 megabytes, but you have 2 memory blocks of it, and 32 to 64 megabits of flash memory. I think it has the 64 on that, and LED indicators, and your USB programmer. Lastly, we have the GoAI A55 development board. This is a 55K lookup table board targeting the 484 BGA package. You've got your camera, IMU, and microphone as well. You've got your HDMI RX and TX ports. And then in this case, we have an external 4 megabytes of PS RAM, just to kind of show some different environments of how you can set up your system. Sometimes in the larger package, it may make more sense to have a external memory because you have a little bit more board space in those type of scenarios. This is just showing our Little B product line and the different devices in it and where the GW1NSR4 fits within that product line and fits within the product lines that Gowin has to offer. And then this just shows our GoAI software development platform roadmap, specific for GoAI, but we also are trying to leverage this in some other areas. So at Gowin, we have a kind of mentality with our GoAI program that is one click to Edge AI. And what that means is that we try to provide the scripting necessary for you to see the entire design flow all the way through. So starting with Ubuntu, we provide we're working on providing a Docker file which sets up a VM in Ubuntu, runs TensorFlow for a particular model. You can choose to train or not train the model, either grab pre-trained files or train it, depending on what you want to do, and then convert that through TensorFlow Lite to the flat buffers file, and then parse that flat buffers file to target um, a Gowin FPGA like the GW1 and SR4. So demos and examples. Currently, we have a Hello World demo, which takes input value and predicts an output value, which would be the sign function of that input value. So for a given value, input value X, what is the sign of X? And that's just a kind of getting started demo so you can see how machine learning works for those that need that, and how our environment works. We have a person detection demo, which uses a camera input, can also use an HDMI input on the larger boards. It detects if there's a person present or not present, and this uses a standard model, a 27-layer model, MobileNet V1. Similarly, we have a car detection demo. This is in progress, this car detection demo. It's not quite done yet, but this will use the HDMI input on the AR18 and A55 boards, and it takes that HDMI input and detects if a car is present or not. So we just retrain the same model, MobileNet V1 model, for car detection instead of person detection. Also, we have an audio phrase detection demo, and this demo detects if somebody says yes or no, and it uses the microphone input to do that. Pre-processes that microphone data with a creating a spectrogram, and then processes that through a machine learning model. And lastly, we're working on, we don't quite have yet, but a gesture detection model. And what that will do is it will use the accelerometer that's on the board, and you can hold the board and do gestures in the air with the accelerometer movement and have those gestures detected. So a W, a O, or an L, these different shapes, it can detect those. So this is just showing the Hello World demo, and you can press play on the PowerPoint and watch the LEDs roll in a sine wave. It's showing in the middle here the model, so it's a small model, and this is using just an input value. It's showing the predicted sine value with real data. So it predicts a sine wave based on that input. This is just taking a X value that's 8 bits and incrementing it, and then looking at the resulting output data of the convolutional neural network. Next is our key audio phrase detection keyword demo. And this is an older board, but the newer board has the microphone built in. This actually uses a convolution, depth-wise convolution, and a fully connected layer. On the left side, you can see the model, and detects if somebody says yes or no, or it can be retrained for other demos as well. We have just a picture here of our person detection demo. So this is using MobileNet V1, which is a much larger model. And this uses camera input data and then outputs via HDMI the video stream, and then has a text overlay that says person if a person is in the image. Just some benchmarks, because sometimes this is kind of important. Some people want to see benchmarks. So for MobileNet V1, we run at about 160 milliseconds at 50 megahertz with FPGA clock speed. This is running MobileNet V1, 28-layer model, and up to 36 kbytes per layer in that model. We're using the COCO dataset. And really, for our applications, since we're targeting a very, very low cost, very low power, very small form factor device, this is good enough. I mean, you can detect a person in less than 200 milliseconds and send that downstream to determine what to do from that. So just to summarize a little bit, the reason why Gowin is interested in machine learning is because we see the number of IoT and edge devices increasing very rapidly, and we see this ecosystem increasing very rapidly as well. And we have programmable parts that are very good at doing these types of computations. And so, you know, we see that localized intelligence, the ability to um, have intelligence locally battery powered is becoming increasingly important for both connected and unconnected systems. Devices that are not connected to the internet and devices that are. So GoAI provides the ideal solution with the machine learning processor and the software tools to provide that localized intelligence. And so there's a variety of links here, our GoAI webpage, our GitHub page, and our frequently asked questions. And if you have any questions, you can definitely reach out through our inquiries page at goinsemi.com. Thank you very much, and look forward to helping you go win by programming for the future.